Hello everyone. In this video, I want to talk about the 4-bar mechanism and the position problem of that, which is basically if this is a 4-bar mechanism and I have given you the size, the length of the link A, B, C, and D, and the input angle theta 2, let's say that's the input angle, then I ask you to find me theta 3 and theta 4, correct? So that is the problem. And what I want is an analytical solution, not numerical solution, because if we move forward with our equations, look, so what we do is basically we add the delta x's and delta y's that each member brings in, and you see these members form a loop, right? So we can say that sum of the total delta x and delta y starting from O2 going through the loop and coming back is 0. Or let's say we can, the other way that I did it here is you can go from O2, one way go to O2 to B through these two members, the red and green. The next method that you go from O2 to B is go to O4 and then go to B. So go through the ground link and the gray member. Okay, and say that the delta x and the delta y of going from O2 to B through either one of these paths is the same. So that's what you have here. A cosine theta is basically what? It's the delta x of this member, right? So if you project it, that's this distance. This is A cosine what? Theta 2 plus B cosine theta 3, which is this distance here, right? This is equal to what? This is equal to, so that's the total delta x going from what to what? Going from O2 to B. One way is to add these two together. The other way is, no, I add this whole D, which you can see here, right? I add this whole D plus what? Plus this distance here, which is basically c cosine theta 4. But in this case, theta 4 is bigger than 90 degrees. Cosine of it is negative. So when I add c cosine theta 4, it's like really I'm subtracting that distance from D, which again gives me this total what? Distance, right? So you see this equation is the total delta x through either path from O2 to B equal. And then you do a similar thing for the y's, right? So you say a sine theta 2, which is this distance, right? Plus b sine theta 3, which is this one. So you say sum of these offsets, these y offsets, is equal to what? Is equal to c sine of theta 4. Now in this case, the ground member is completely horizontal. So that is equal to what? C times sine theta 4, which is this distance. So you said this guy is equal to sum of those two, and this is your second equation. Now, if you look at your equations, clearly see these two equations where theta 2 is known and the ABCDs are known, and theta 3 and theta 4 are unknowns. These are nonlinear equations, and if we want, we can solve them numerically, but you know, numerical methods, first of all, they don't tell us anything about the effects of A, B, C, and D on the solutions and the final results. And of course, you always need to make sure that your algorithm converges and so on. So, and you have some initial guess. So is there an analytical way to these nonlinear equations, which, by the way, if you ever hear this word, let me add this word for you. So these guys are called transcendental equations. Okay, so if you ever hear this term here, transcendental, I just want you to know what they are, and these equations are what we call transcendental equations. These are nonlinear, and is there a solution to them? Yes, fortunately there is, and that's what I want to show you. So what do I do? If I call the top equation 1 and the bottom equation 2, what I will do is, the first thing, I bring this D on the top equation to the left side, and then this B cosine theta to the right side, so they both become negative, as you can see. the bottom equation also, I bring this b sine theta 3 to the right side, so it becomes negative b sine theta 3. So I rearrange and rewrite this 1 and 2 into 3 and 4. Of course, these are still nonlinear and I have not done anything. Why did I do it that way? The reason is now I brought both of my unknowns to the right side and my left side is completely known because I know A, I know D, and I know theta 2. Theta 2 is given. So now I've written my equations into all the unknowns on the right, all the knowns on the left, or I can reverse it and say the right hand side is all known. Now what do? I square both sides of 3, I square both sides of 4 and add them together. You might say, why would you do that? The reason is you have sines and cosines with the same coefficient. You see A here, you see the same thing B here, right, or negative B, and you see C here. So when you square them and add them together, you'll get sine squares plus cosine squares, which will be 1. So for example here, when I square this, what do I get? I get a squared cosine squared of theta 2 plus d squared minus 2ad cosine theta 2, and here I get a sine squared theta 2. Now that a cosine squared that I had from the top and this a sine squared I have from the bottom, when I add them together, I simply get what? A squared. That d squared is already there, you can see it, and then negative 2ad cosine theta is this term. So clearly you can see that, or this guy here on the top. This here is sum of the two left-hand side of these two equations squared and added together. What do I get on the right-hand side? Well, I will get these terms individually squared. So I get b squared cosine theta 3 squared and b squared sine theta 3 squared, which when I add them together, I get b squared. These two other terms, c squared cosine squared theta 4 and c squared sine squared theta 4, will give me c squared. And then I have that 2 times term. So what is on the top one? It's going to be negative 2bc multiplication of the cosines, or the product of the cosines. And again, negative 2bc on the bottom one, the product of the sines. So I can factor out that negative 2bc from both of them. And what is remaining is the product of the cosines plus the product of the sines. Now what do? I bring these two constants to the left-hand side, because now my left-hand side is entirely known. It's based on the size of the links and angle theta 2. On the right-hand side, I use the trig identity, which says cosine A cosine B plus sine A sine B is cosine of A minus B. And this is exactly what you see I have done here. So that is cosine of theta 4 minus theta 3, or theta 3 minus 4. They are the same thing, right? Cosine is an even function. So now I got this equation, right? Now what can I do? I can divide the left-hand side by this constant negative 2bc. And the result is going to be what? Cosine of theta 3 minus 4 minus 3. And this is exactly this ratio that you can see here. I give it a name and I call it S. Right? Now, cosine of theta 4 minus 3 is S. What is sine of theta 4 minus theta 3? Well, if cosine of something is S, sine of it is square root 1 minus what? S squared plus and minus. And when I have sine of some angle and I have cosine of some angle, using arctangent 2 or arctangent in general, I can find what? I can find that angle, right? Here, this angle alpha is exactly what? Is exactly the difference between theta 3 and theta 4, right? So if I call theta 4 minus 3 alpha, or theta 4 theta 3 plus alpha, cosine of that alpha, as you can see, so this term inside the parentheses, I called it alpha. Right? The cosine of that alpha is S. The sine of it is square root 1 minus S squared plus minus. So using the arctangent 2 command or arctangent command, I can find what? I can find alpha. So this alpha again is the difference between 4 and 3. And you see I can easily calculate it using an arctangent command and with this constant ratio where everything for it is known. Good. So now I know the difference between 4 and 3. I don't know 3 and 4 yet, but I know how much is the difference between them. So now what do? Now I use this result, which is theta 4 is theta 3 plus alpha. I plug it back into equation number 2, one of my original equations. Okay, I plug it into 2, or I can plug it into 4, doesn't matter. I can plug it into 4. Why do I do that? Because now theta 4 will be eliminated. Theta 4 is going to be replaced by theta 3 plus alpha, so my result is going to be this. Look at this equation. If you can see this equation, the only thing it has is now theta 3. It's just one equation and one unknown. So now 2 equations, 2 unknown is down to 1 equation and 1 unknown. Still not a linear equation. It's nonlinear in terms of theta 3. Remember, alpha is just a constant angle. So still nonlinear in terms of theta 3. So how do we solve that? I'll show you. But you see, now I brought it down to 1 equation, 1 unknown. Now what do? I expand sine theta 3 plus alpha. As you know, sine of a plus b in general is what? Sine alpha cosine beta plus cosine alpha sine beta. So if I do that, then cosine alpha is going to be multiplied by what? Multiplied by sine theta, right? Cosine alpha is going to be multiplied by sine theta, and then sine theta 3, and then here is another sine theta 3, so I can factor sine theta 3 out. There will be a negative b left, and there will be a c cosine alpha. So here I guess I need to add a c cosine alpha. On the other hand, I also will have a c cosine theta sine alpha. So again, here there is a c that I should add, right? So it's going to be c sine alpha cosine theta is equal to the right hand side or left hand side, whatever you want to call it, a sine theta 2. Now look at this. So I just rewrote, all I did, I rewrote that top equation into the form of this what? This bottom equation. Still, again, one equation, nonlinear in terms of theta 3, because I have both sine and cosine of theta 3 in it. But fortunately, this type of equation, which is like a constant times sine of the angle, plus another constant times cosine of an angle, equals another constant, this equation in general, there is a solution for that. And what would you do to solve it? One of the methods for solving this equation 7 is to use tangent of half angle. So for sine of theta 3, we replace it by 2 tangent of theta 3 over 2 over 1 plus tangent square of theta 3 over 2. And then for cosine of that, I replace 1 minus tangent squared of half angle over 1 plus tangent square of half angle. If I plug them back into 7, what do you think you will get? Well, let's take a look. So here I plug those two identities into this equation 7, plug 8 and 9 into 7. So this is my equation now. And I multiply both sides of it by the denominator, the common denominator, and then rearrange it in terms of tangent square and tangent and constant. And so now if you look at this equation, it is going to be a quadratic equation, right? There is tangent square times a constant value, right? You know alpha is constant, theta is constant, or theta 2, they are given to us. So that whole term, that is the coefficient of tangent square of half angle theta 3, that is just a constant or a known value. The term that is multiplied by the linear tangent theta 3 over 2, this term is also a constant. And then this term, that is just a constant term, not multiplied by anything. So clearly you see that is k1 something squared plus k2, that something plus k3 equals 0. That's a quadratic equation. From this formula, we can easily get what? From the solution of quadratic equation, I can get the solution for the unknown, which in this case is tangent of theta 3 over 2. So theta 3 over 2, right? This guy is going to be this term inside the parentheses. Now that's tangent of theta 3 over 2, so we need to take an arctangent to just make it theta 3 over 2, and we need to multiply it by a 2 to make it what? To make it theta 3. So there we go. This is your theta 3 in terms of k1, k2, and k3, which are all given values. They are constant values. And you see, k1, k2, k3, again, they are in terms of a, b, c, d, alpha. alpha itself is a constant here. And once I know theta 3, guess what? Theta 4 is theta 3 plus alpha. So just whatever this theta 3 is, add alpha to it, and you will get what? Theta 4. And clearly you see that there are two solutions, right? There are two solutions for theta 3 and theta 4. And you know, always for one given angle, there are two versions. One is the solution that is going like this, and the other one that is basically something like this. If I can draw it properly, hopefully. So it is something like this. You see? So it's not going to be the members like this. This is the second configuration. So this gray member is going to be like that. The green member is going to be like this, and the red member stays. So there are two solutions in general, and you clearly can see the solutions here. So hopefully this video was useful to you. This is one of those problems that is quite common in dynamics or mechanism synthesis and analysis. The analytic solution to the 4-bar linkage mechanics. So here I changed this title for you. It's the analytic solution to the 4-bar mechanism position problem. Otherwise, there is always numeric solution to equations 3 and 4, or to 1 and 2. Okay, so hopefully this video was useful to you, and I'll see you in my next video. Thank you.